Hello students, welcome to EPG Pathshala. I am Dr. Maimuna Akhtar from School of Pharmaceutical Education and Research, Jamia Hamdard. Here we are discussing about the module Application of Fluorescence Quenching, in specific application to biological systems from paper Atomic Spectroscopy. After completing this module, you should be able to understand the fluorescence application when quenching of fluorescence is used. We have slightly brushed up the fluorescence quenchers, and then discussed in detail about the quenching of about the application of quenching to membranes, quenching resolved emission spectra. Now, first brushing the concept of fluorescence. Fluorescence is a process of emission of excess of light by molecules after they have absorbed light. That means they release this excess of energy in the form of light. So we already know that fluorescence is an immediate phenomena, which means the fluorescence stops as soon as the light which is incident on the molecule is stopped. The property of fluorescence has been used to study various properties of the molecules. Not only the fluorescence, but the methods of decreasing the fluorescence, which is known as quenching of fluorescence, has also been used for study of different phenomena, different properties, like study of chemical and biological phenomena in research. So quenching of fluorescence means that you add some agent, or due to some other reason there is decrease in the fluorescence of the molecule. And the reasons for quenching may be that there is some reaction in the excited state of the molecule, thereby it loses energy in other forms, not releases this excess energy in the form of light. There can be molecular rearrangement in a molecule, thereby losing the property of fluorescence. The collision between the molecules also lead to the decrease in the fluorescence. Energy transfers, charge transfer reactions, or maybe photochemistry is responsible for quenching of fluorescence. Also, due to formation of complex in ground state has led to quenching of fluorescence. This phenomena of quenching of fluorescence has been widely studied, both at fundamental level, that means you study what affects the quenching, what affects the fluorescence, and as a source of information about biological systems. That means you already know that there is a system which fluoresces. You add some quencher and study actually what happens and which is fluorescing, in what conditions it's fluorescing. You can actually study those biochemical systems. These biochemical applications of quenching are due to the molecular interaction that result in quenching. Fluorescence quenchers. We already know what is fluorescence quenching. We have also discussed the same in the last module. Fluorescence quenchers are those substances which act as quenchers of fluorescence. It means they block the fluorescence or they reduce the fluorescence. Best known are collision quenchers, as we already know. And among the best collision quenchers is the molecular oxygen, which quenches almost all known fluorophores. Depending upon the sample under investigation, the different quenchers can be used. Like aromatic and aliphatic amines, they act as efficient quenchers for unsubstituted hydrocarbons. For example, diethylaniline. It effectively quenches the fluorescence of anthracene because of formation of excited state charge transfer complex. So heavy metal quenching is also known, and the phenomena is due to the presence of iodine or bromine. For example, trichloroethanol, bromobenzene, they act as efficient collision quenchers. Some other examples are indole, carbazole, and their derivatives. They are uniquely sensitive to quenching by chlorinated hydrocarbons and by electron scavengers such as proton, histidine, cysteine, nitride group, fumarate, copper, lead, cadmium, and manganese ions. Fluorescence of indole or tryptophan and its derivatives are affected by acrylamide, succinamide, dichlorestamide, dimethylformamide, pyridinium hydrochloride, or imidazolium hydrochloride, methionine, silver, and cesium salts. In this module, we'll be focusing on application of quenching of fluorescence. Like you can use the study of fluorescence for various reasons. We can also use the process of quenching of fluorescence for study of different biological systems, for study of the proteins, for study of the membranes, the transport system in membranes, the localization of particular amino acid in membranes, because the conformation and dynamics of proteins are very important for biological action. So you can study those important factors or important parameters by using quenching of fluorescence. For example, as I mentioned, in addition to the identification of amino acids that show fluorescence, we can also see diffusion coefficient of oxygen in membranes, because oxygen is very important for life system, and its transport across the membrane is also important. So it can be studied through this technique. We can also study the position of quenchers. By studying the position of quenchers, we can actually study the fluorophores in the protein systems. Quenching resolved emission spectra have also been studied, and they have also been used in study of membranes and other proteins. So application of quenching can be used in many ways. So we have described here its application in the study of membranes. So it can be applied for study of oxygen diffusion through membranes, oxygen diffusion in various conditions, localization of membrane-bound tryptophan residue. That means you actually want to know the position of tryptophan molecule in the protein. You can use the quenching technique to localize that tryptophan molecule. You can also use these quenching techniques for membrane probes to localize where the quencher actually affects. A parallax and depth dependent quenching in membranes has also been studied. We can also study the boundary lipid quenching, lipids that are present in the lipid bimembrane. What are the boundary lipids by using this quenching technique? Also, lipid water partitioning of various agents that are used as quenchers or as fluorophores. Their partitioning across the lipid membrane can be studied by studying their lipid water partitioning. And of course, quenching in micelles has been used in chemistry to discuss or to explore various properties of the molecules. We'll be coming one by one, taking up the applications of the fluorescence quenching. The first application we'll touch is the oxygen diffusion in membrane. We all know that oxygen is very important for the cellular function, because in all oxidation reactions, oxygen is required. And oxygen behaves as a very effective quencher for various fluorophores. So by actually studying the quenching of various fluorophores by oxygen diffusion, we can study that how much amount of oxygen can cross the membrane. So quenching by oxygen has been used to determine the apparent diffusion coefficient of oxygen in membranes. This can be accomplished by using various probes. It means they should go into the lipid bilayer and are covalently bound to the lipids. The oxygen Sternworm plot for 2-methyl-anthracene in vesicles of DMPC and DPCC are shown in next figure. They show a phase transition temperature. That means like with temperature, there is a transition in a phase. It's near 24 and 37 has been studied. So the experimental temperature near 31 degrees centigrade, which is a temperature above the phase transition of the DPCC bilayer. And at that temperature, the anisotropic measurements of those bilayers reveal large change in viscosity at the transition temperature. But it was observed that the oxygen diffusion is not affected by change in any temperature. So membranes with high cholesterol are rigid. It is known that if the cholesterol content in the membranes increase, that means fatty part increases, their rigidity increases. They show increased diffusion of oxygen. So in other words, if you see increased diffusion of oxygen, you can actually see that lipid content of the cell is going high. So which has been proven by pyrene dodecanoic acid quenching in erythrocyte ghost membranes. This slide shows you the oxygen quenching of 2-methyl-anthracene at a temperature that is different from the transition phase temperature of DMPC and DPCC. So you can see with increase in concentration, there is increase in the fluorescent quenching of the system. Another application can be the identification of tryptophan residue. We all know tryptophan is an important amino acid for proteins, as it is one of the limiting essential amino acid in protein metabolism. Tryptophan serves as precursor for the synthesis of neurotransmitters like serotonin and tryptamine. It is also used for the synthesis of antiplegra vitamin, that's nicotinic acid. It is known to play a role in protein structure stability. Therefore, large number of studies are based on tryptophan, and studies have been done to determine the content of tryptophan in proteins. For this, collision quenching technique has been used, and because it's a short range interaction, so the extent of quenching can be used to indicate the amount of molecular contact between the fluorophore and the quencher. This concept has been used to study the localization of tryptophan residue in membrane spanning peptides. Acrylamide quenching of peptides when bound to DOPC vesicle has been studied for these reasons. The study has also revealed that extent of quenching depends upon the strength, and also the position of the tryptophan actually dictates the quenching of the system. So this slide shows you quenching of membrane probes or membrane probes that have been used for localizing quenchers in the system. So there are three different compounds which have been used: bromo-PCA, that is dibromosteric acid, nitroxide labeled fatty acid, and they all show bromine at different positions, which actually determines their efficiency as a quencher. A somewhat more advanced approach has been used to study the quenching of membrane probes. It is quenching that are covalently linked to the phospholipids and thus restrict to particular depth in the lipid bilayer. So you can actually see the localized probes by using this quenching technique. So typical lipid quenchers are the brominated phosphatidylcholines and nitroxide labeled phosphatidylcholines or fatty acids. The term ghost refers to the red blood cell membrane after hemoglobin has been removed from them by using cell lysis technique. The fluorophenyl or fluoronyl probes that are quenched by 9,10-dibromostearate are partitioned into the membranes can be studied by this technique. Since the bromine atoms are smaller, they are expected to be localized according to their position on the fatty acid chain. These bromine atoms are located near the center of the fatty acid, as you can see in the structures on the next slide. So one expects maximal quenching for those fluoronyl groups which are located in deep as a bromine atom. The quenching data reveals large amount of quenching when the fluoronyl group are placed more deeply in the bilayer by longer methylene groups. That means you prepare a fluoronyl quencher by using a longer methynyl group, and that will go deep into the lipid bilayer, and it has been observed that quenching was high in such cases. That means their interaction within the deep is more than on the surface. So hence the fluoronyl probes are located as expected from their structure. So for these fluoronyl fatty acids, a alkyl side chain beyond fluoronyl group was important for probe localization, because that the length of that alkyl side chain will actually dictate the position of that fluoronyl in the lipid bilayer. So this slide shows you quenching of membrane probes or membrane probes that have been used for localizing quenchers in the system. So there are three different compounds which have been used: bromo-PCA, that is dibromosteric acid, nitroxide labeled fatty acid, and they all show bromine at different positions, which actually determines their efficiency as a quencher. This slide shows you the quenching of fluoronyl fatty acids by the 9,10-dibromostearic acid in erythrocyte ghost membrane. We can see with increase in the concentration of the 9,10-dibromospheric acid. Another technique that can be studied and be useful in studying of membrane is parallax and depth dependent quenching in membranes. The basic idea is to compare the amount of quenching observed for quenchers that are located at two different depths in the bilayer. Bilayer means the lipid bilayer of the cell membrane. The distance of the fluorophores from the center of the bilayer, which is mentioned or you can say denoted by ZCF, is then calculated from the equation. ZCF is given by LCl plus the negative log of the fluorescence ratio divided by the pi c with less value of the L21 multiplied by twice L12. The L21 is the difference in the depth between shallow and deep quencher. The shallow quencher is located at a distance, that is LCl, from center of the bilayer. C is the concentration of the quencher in the molecule per unit area. F1 and F2 are the relative intensities of the fluorophore in the presence of the shallow and deep quenchers. The location of the fluorophore can be determined by using two quenchers. So this analysis yields a single distance and does not reveal a distribution of fluorophore depth if such a distribution is present. It shows the dependence of the KSV, the apparent stem Volmer quenching constant, on n the number of methylene units in the prenyl acyl chain for bilayer with different bromine PC quenchers. The subscript X and Y indicates the location of the bromine atom. The bilayer consists of 1 palmitoyl 2 oleoyl phosphatidylcholinees with 50% mole cholesterol. So for determining the position of the fluorophore, you need to have actually two quenchers, and from the distance of the two quenchers, you can determine the depth of the fluorophore. For example, in case of protein, the fluorophore is your tryptophan. We can also study the boundary lipids. Boundary lipids are those lipids which are at the boundary of the the membranes. Boundary lipid membrane quenching has also been studied. For example, you suppose if you have a protein that is surrounded by a discrete number of lipid molecules and that tryptophan fluorescence is accessible to quenchers in the membrane phase, then the number of boundary lipid molecules can be estimated. And it can be estimated by a given formula, F minus F minimum to F naught to F minimum, and can be given by 1 minus Q. Q is quantum yield, N is number of the molecule. And F0 is the intensity in absence of the quencher, and F minimum is the intensity when the probe is in pure quencher liquid. F is the intensity at given mole fraction of quencher liquid. So this model was tested using small probes in membrane and for calcium ATPase, which is a large membrane bound protein containing 11 to 13 tryptophan residue. For tryptophan octyl ester, the intensity decreased according to n equal to 6. That means n a number of the molecules, indicating that each tryptophan was surrounded by 6 lipid molecules. So for calcium ATPase, the intensity decreased with n equal to 2. This does not indicate that only 2 lipid molecules surround the protein, but that only 2 lipid molecules are in contact with tryptophan residue in calcium ATPase. So you have to be careful in analyzing the results also. So similar results of 2 boundary quenchers were found for the calcium ATPase using 1,2-bis-9 10-dibromyl olyl phosphatidylcholine to study the positioning of the proteins and the lipids surrounding. This is the figure, a plot showing quenching of tryptophan, octyl ester and the calcium ATPase. So with increase in the concentration of the quencher, we can see a decrease in the fluorescence. So effect of lipid water partitioning on quenching. We can see if a molecule is soluble in both lipid as well as in water, that means it will distribute in water and lipid according to its solubility. So the concentration will vary according to the environment. So concentration of quencher in the membrane were known for the amount of quencher that is added. So however, there are many instances where the quencher partition into the membrane but some fraction of quencher remains in the aqueous phase, because that, as I said, it depends upon the solubility of the quencher in lipid as well as in water. So consequently, the amount of quencher added, you expect that goes into lipid does not happens because of its water solubility. So is not and you cannot determine simply the amount of quencher in the membrane. Therefore, you need to actually look into the total lipid concentration of the sample or lipid solubility of the sample. The effect of lipid water partitioning can also be studied, as I told, that in these cases it is necessary to determine the lipid water partitioning coefficient to interpret the observed quenching. For example, a quencher that distributes between the membrane and aqueous phase at non-saturating concentration of quencher, the concentration in the water and the membrane phase are related by partition coefficient. We already know partition coefficient means when a solution containing a solute comes in contact with another liquid which is insoluble with the one, the solute that is present distributes itself between the two layers in a fixed ratio. So this quencher also behaves as a solute, and when it is in lipid phase and comes in contact with the aqueous phase, it distributes itself between the two layers, and the distribution is a fixed ratio. And let's suppose this quencher distributes between membrane and the aqueous membrane at non-saturating concentrations, and we can determine the partition coefficient by normal simple equation, which is according in organic, and you write C aqueous over C organic. Here we can write quenching in the membrane to quenching in water phase. The successful determination of quencher diffusion and partition coefficient requires that the range of lipid concentration results in a range of fractional partitioning of the quencher. The fraction of the quencher partitioned in the membrane is given by equation Fm equal to P prime M oblique P prime M plus 1 minus prime M. This slide shows you the dependence of the NBD on the partitioning of the NBD between membrane and the quenching of fluorescence can be very complex in micelles. We can see in the figure above that quenching of pyrene in methanol by a lipid-soluble pyridinium derivative, which probably quenches by a charge transfer mechanism, is increasing with increasing the concentration. So when the quencher C16PC is added to methanol solution of pyrene, the lifetime decreases but remains a single exponential. But when pyrene is bound to micelle and lipid-soluble quencher are added, the decay time becomes strongly multiple exponential, because then this quencher can go into the micelle and thereby affect the pyrene in the bound form of the micelle. These decays are not typical of collisional quenchers in solution, as seen from the decay at long time about 200 nanoseconds. The decay time of this component is the same as pyrene in micelles without quenchers. The complex pyrene intensity decay seen in figure on next slide are due to position statics in quenching binding to the micelles. Under these conditions of experiments, there are average of less than one quencher per micelle. So hence some of the micelle contained a quencher and some did not. So micelles without bound quencher display the lifetime of unquenched pyrene. The micelles with quenchers display a shorter lifetime. For such a system, the intensity decay is given by equation I, which is intensity, to I naught within brackets minus T oblique tau naught eta exponential of Q KQT minus 1, where tau naught is the unquenched lifetime, eta is the mean number of quenchers per micelle, Kq is the decay rate due to a single quencher molecule in the micelle. These graphs show you the quenching of pyrene in methanol solution and in STS micelles. We can see in the graph on the left hand side that the decay is very fast when you compare to the decay in the STS micelles. And also in two cases there is no quenching. The green slide shows you no quenching compared to the SDSE, where the purple line which shows you the quenching in the micelles. Lateral diffusion in membranes. We can also study the lateral diffusion in membranes by studying the quenching of the fluorescence. The theory of two-dimensional diffusion in membrane is complex because The mechanism of diffusion itself is very complex to understand because it is affected by number of factors like the size of the molecule, concentration. So analytical expressions are now available for time-dependent decay of fluorophores in membrane with the quenchers constrained to lateral diffusion in 2 dimensions. The time-dependent decay expected for Somolowski quenching in 2 dimensions and for the radiation module have been reported. For the usual assumption of instantaneous quenching on fluorophore quenchers, a fluorophore quencher contact, the intensity decay is given by the equation mentioned. In the expression, gamma is the reciprocal of the unquenched decay time, Q is the quencher concentration in molecule, R is the interaction radius, and tau is radius divided by the mutual diffusion coefficient, and J0 and Y0 are zero order Bessel functions of the first and second kinds, and it requires even more complex expressions for the radiation models. Therefore, quenching models have been preferred over radiation models. Quenching resolved emission spectra. Emission spectra are studied for the functioning of the proteins, and we know that emission spectra of proteins often shift in presence of quenching. So therefore, quenching can be used to resolve the protein emission spectra. And this actually occurs, the shifting of the protein emission spectra occurs due to the exposure of tryptophan molecules differently to the quencher. So if a solution contains 2 fluorophores with different Stern-Volmer quenching constant, it will show different amount of quenching at each wavelength. That depends upon the amplitude of the emission spectra. This is accomplished by measuring a Stern-Volmer plot of each emission wavelength. For more than one fluorophore, the wavelength dependent data can be described by the equation, where Fi is the fractional contribution of the ith fluorophore to steady state intensity at wavelength lambda to the unquenched emission spectra. Ki is the Stern-Volmer quencher constant of the ith species at wavelength lambda. This graph shows you the steady state emission spectra of DPH and 1 AEDANS in 1.2 millimole SDS micelles. The use of quenching to resolve emission spectra is illustrated by this example. DPH is not water soluble, so the DPH is expected to dissolve in SDS micelles, whereas AEDNS is water soluble and negatively charged, so it is not expected to bind to negatively charged SDS micelles. Hence, this AEDNA DANS is expected to be quenched by water-soluble quencher, acrylamide, and DPH is not expected to be accessible to the acrylamide quencher. Acrylamide Stern-Volmer plot for the separate solutions of DPH, SDS, and AEDNS can be observed in such cases. So this has been experimented in the resolved emission spectra of the E. coli TET repressor. The TET repressor from E. coli is a DNA binding protein that controls the expression of gene that confers resistance to tetracycline. This protein is a symmetrical dimer that contains true tryptophan residues in each subunit at position 43 and 75. W43 is thought to be an exposed residue, and W75, that is tryptophan of position 43 and tryptophan of position 47, is thought to be buried in the protein matrix. So iodine Stern-Volmer plot for the TET repressor were measured for various emission wavelengths. A large amount of quenching was observed at longer wavelength. So when analyzed in terms of two components, one of these components was found to be almost inaccessible to iodide. So this shows you the three-dimensional structure of the E. coli TET repressor, and on the right hand side is the plot of Stern-Volmer plot for iodide quenching of E. coli TET repressor. In the plot you can see that the W75 quenching is very less, that means this is inaccessible to the iodide. We can see various association reactions with quenching, and quenching can be due to very specific binding interactions. Quenchers that are in solutions or that interact in solutions with the micromolecules but did not display any specific interaction. They it can be a bundle of two peptide chains. Like each peptide chain contains two alpha helix region and single tryptophan residue. The emission is strongly quenched by even low concentration of halothane. So we can see, depending upon the amount of the tryptophan in your protein molecule, the quenching and the association reactions can be correlated. The quenching of tryptophan residue was also examined in presence of 50% trifluoroethanol. So trifluoroethanol is known to disrupt hydrophobic interaction but to enhance helical formation in peptide. In 50% TFE, the peptide is exposed to exist as two separate alpha helical peptides that are not bound to each other. These results show that tryptophan residue are buried in a non-polar region in the 4-helix bundle and become exposed to the solvent phase when the two peptides dissociate only. One of the methods is to calculate the apparent bimolecular quenching constant and tryptophan fluorescence intensities of the 4-alpha helix bundle in presence of the halothane. So it's time to summarize, students, what did we learn about the fluorescence quenching in this module. So in this module, we briefly brushed up the basic concept of fluorescence and quenching of fluorescence, the different quenchers that are used as quenching agents. The application of this quenching technique specifically to the membranes, like studying the oxygen diffusion in membranes and its importance. We also discuss about identification of fluorophore positions, like tryptophan position, identifying tryptophan position in proteins, and about the boundary lipids by using quenching technique. We also discussed the effect of the lipid water partitioning on the concentration of the quenching. Lateral diffusion in membrane and quenching also was discussed along with the result emission spectra. Very briefly, we discussed about the result emission spectra. Thank you.